Now you can hear me, I guess. Hello, everyone online. Thanks, Maria Sole, for this nice introduction, as well as to the entire nanotalks team for inviting me. It's a rare and nice opportunity to bring our research to a wider audience. And I'm emphasizing our research here because I'm lucky to be part of a very collaborative team, which includes Johanna Malle and Claire Webster. And in the process of discussing tonight's talk with the nano teams, we ended up on topics that are actually largely their expertise. So I'm very happy to contribute to this work, but the merit of what I'll show is actually mostly Johanna's. And so just as a background, okay, sorry, just as background, we are part of the snow hydrology group at SLF, and the group is mainly interested in snow as a part of the hydrological cycle. So we study the processes that control how the snow accumulates and how it melts. And we're interested in how these processes vary in space and time, especially also in forests, because that's where they are most complicated. And our work then directly feeds into snow models that are used by our group to do forecasts of the snow distribution and the snow melt over entire Switzerland and throughout the whole winter. And this is a service that we provide to BAFU and so indirectly to the public. But today, I'd like to look at our research from a somewhat different angle. So I'd like to give you sort of a glimpse into a day in the life of a forest snow scientist. How do we work? What do we look at? And this is now not in a hydrological context, but within the context of this big topic of climate change. And so we'll start by looking at why we care about snow and forests in the context of climate change, or better, why we need to look at snow and forests carefully if we want to understand and predict how the climate is changing. And then I want to try and explain why this is a complex problem and why the drones can really help us in tackling this problem. And finally, I'll show you a specific example from our science, from how we use drones to study forest snow. This is from Johanna's PhD project. So let's start with really my favorite bit, snow. Now, snow is really a most fascinating material. It's extremely complex, and everyone who does backcountry skiing knows that it can change really, really quickly. And as I summarize it here, snow is a hot material that keeps our Earth cool. So that may sound a bit weird, but it's actually really what it is. Snow is bright white, and that means that it reflects most of the incoming solar radiation back to the atmosphere. This can be up to 98%. And this obviously drastically limits how much energy can be absorbed by the Earth and contributes to warming. But at the same time, snow is really hot. So from a physical point of view, a hot material is a material that is close to its melting point. And with snow, that's the case very often. And unfortunately, this aspect also means that snow is very climate sensitive. So a small increase in temperature can mean a transition from snow to rain in many places and very often. Then forests are also very important for our climate. One of the main reasons for that is that they act as massive carbon sinks. And that's not just because the trees do photosynthesis, but also because forests soils store huge amounts of carbon from decomposed material that has accumulated there over the millennia. And at high latitudes, this carbon is locked into so-called permafrost, so permanently frozen soil. And now the forests are experiencing pretty drastic and rapid changes. You will have heard of that wildfires are becoming more frequent. Another example is widespread tree mortality because of insect infestations. And the combination of forest loss and also thawing permafrost is both reducing the capacity of the forest to take up carbon and also causing massive carbon release to the atmosphere in form of methane. And so now these are two important players. And in our research, we're interested in a phenomenon that involves them both. And this is the so-called snow albedo feedback over forests. I should say here that albedo is the fraction of the radiation or the incoming radiation to a surface that is reflected back to the atmosphere. And so generally, this snow albedo feedback describes a positive feedback loop by which you have an increase, an initial climate forcing, which in our case is man-made, and this causes an initial temperature increase. And this increase in temperature will cause snow extents to decline, so less snow, we will have a darker surface. A darker surface can absorb more radiation, and so this will cause more temperature increase. And this positive feedback loop is now leading to something that we call Arctic amplification. So it's a phenomenon that we are observing now. The Arctic regions are warming at a much, much higher rate than the global average. And now the boreal forest is part of these high latitudes, and it actually covers a large surface area in these high latitudes, and there the trees mask the snow surface. So this complicates this albedo feedback, and it has been shown that this is a large uncertainty of our climate models. And so this uncertainty, of course, arises because on the same surface, we combine highly reflective snow and very absorptive trees. And as you can see here, this variability is really the challenge. So these pictures are showing the main scene on 3 different days. You see that we have snow in the trees that has specific properties. We have sunlit snow, we have shaded snow, we have snow-free trees that absorb much more radiation. Then we also have snowpack evolution. So at some point we will have partial snow cover. And it's really not a surprise that models struggle to capture the albedo of such a scene, because so these climate models are really complex and they need to somehow simplify the processes that are going on. And so models assume that the forest is just a homogeneous layer, and this obviously does not correspond to a real forest structure. And now the issue is that it's really hard to quantify how much this simplification will affect the accuracy of the model, because we cannot really observe the important processes at the scales at which we need to model them. And now, again, using our example of surface albedo, we can measure it by installing a tower with sensors that look down at our forests, but then we will just see one point in space. Or we can use satellite data, which covers a very, very large area, but then it's really difficult to disentangle what's going on. And so our observational basis to tackle this albedo over forests problem is not really good. And now that's where the drones come in, because drones are gaining huge popularity in the geosciences because they offer us new perspectives and they offer us a lot of flexibility. So we can acquire data when and where we want, pretty much. And they allow us to see a lot of detail because we can fly close to the surface, but at the same time, they allow us to cover much, much larger areas. So to refer back to the example I just mentioned, they perfectly bridge the gap between the sensor on the tower and the satellite. And here I'm just showing 2 examples of drones to give you a bit an idea that the drones are not just drones. So the one that you see on the left is a commercial imaging drone, and that's quite easy to operate. It's quite cheap and it has a long flight time. While on the right, you see a multicopter. It's a very heavy drone. It carries a very expensive instrument. It's, the drone itself is much more expensive, and to operate such an instrument, you need a lot of practice and not a lot of experience. And with this, I also want to say that while drones bring a lot of new opportunities, they also bring a lot of new challenges. And so, especially for us working in cold environments, we are pretty much always operating at the range limit of the specifications. So we work at high latitudes where the GPS signal is more difficult to get. We work in the cold where the battery life is reduced. So it's not straightforward. And also very often we want the drones to do something that they're not made to do. So the off-the-shelf solution doesn't really work. And suddenly a natural scientist needs to become a bit of an engineer as well. And finally, I should also mention that the popularity of recreational drones is becoming a bit of a problem. So now if you're in the mountains hiking, you'll very often see people just operating their private little imaging drones to take cool videos or pictures. And this increase in use of drones is really requiring new regulations. And that's also what's going to happen in Switzerland this year. So Switzerland will be adopting a new EU regulation that requires drone pilots to be registered and also to take a test. So now we're set up to look at a bit of science and how we have applied this new opportunity that drones are bringing to our research. So to illustrate the problem, here we have our complex forest structure, and we want to understand the land surface albedo, which is given as the fraction of outgoing shortwave radiation divided by the fraction of incoming shortwave radiation. And so our idea was to use a drone to perform measurements that would allow us to disentangle the different factors that control land surface albedo. And then like that, we would have a data set that would allow us to check if the model capture these effects. And so Claire and Johanna designed this albedo drone. So that's a commercial octocopter. And you see that they equipped it with 2 shortwave radiation sensor, one looking up and one looking down, and also with a camera with a fisheye lens. On the right, you see how the drone looks when it's in the air. And now the measurement principle of this instrument is that, so we would fly it over forests with varying forest density, and it would always hover at specific waypoints, and one waypoint is a measurement. And one measurement includes an albedo measurement, which is obtained by just relating the measurements from the 2 shortwave radiation sensors. And it would also include a hemispherical image. This image captures exactly the same perspective as the sensor, and it allows us to characterize the ground conditions co-located to this albedo measurement. And now, because this drone is such a flexible tool, we flew it on many days in different places, in Switzerland, in Finland, with different meteorological conditions. And really, this allowed us to create a data set where we could disentangle, or we could look at individual effects of the ground conditions on the albedo. And as next, I'm just going to show you a few examples of what we got. So in this plot here, you see the measured land surface albedo on the y-axis, and on the x-axis we have the fraction of visible snow on that we could obtain from these images. And now the points include measurements along the same transects, but on 4 different days, as marked by the symbols and the colors. And on the images on the right, you see the example of one waypoint and how the snow cover changed over these 4 measurement days. And now this helps us interpreting the plot. So we have a very clear increase in land surface albedo the more snow we see, and we will have also more variability in albedo across our site on days with full snow cover, while if we only have very little snow, as you see with the green points, the albedo is very limited in the first place. So that's the example of how visible snow impacts land surface albedo. But then on top of that, so we have again a similar plot, land surface albedo plotted against visible snow fraction. And now the colors denote whether we have snow in the trees or not. And so the systematic increase of land surface albedo in the presence of interception shows us how this is an effect that we have on top of the visible snow on the ground. So we have systematically higher land surface albedo when there is snow in the trees. This is just a qualitative assessment because tracking snow in the trees with image analysis is really difficult. And now finally, here we have 2 plots with data collected just on clear sky days on very different sites. So we visited spruce sites, pine sites, needle leaf trees, and deciduous trees. The plots are divided with needle leaf trees on the left and deciduous trees on the right. And now we have again land surface albedo on the y-axis, but now the x-axis is showing the fraction not of visible snow, but of visible sunlit snow. And this is now the nicest linear relationship that we saw so far. And this shows how really the sunlit snow exerts a primary control on land surface albedo. And this is quite an interesting finding because the shadows move throughout the course of the day. So what we're seeing here implies that the albedo at the same location will change throughout the course of a day. And now these are just examples that I showed to show you how we singled out individual factors. And this is really a quite unique data set that for the first time allowed us to check if the models are actually capable of replicating that. And so that's what I would like to link back to now, because we used this data set to actually check a climate model. So I'll just show you an example because this is work that has started now and will continue for a long time probably, because there's a lot to do. So what we're seeing here is, again, land surface albedo on the y-axis, and this is now throughout the course of the day. So the individual colors of the points are different points. We have the green ones that are in very dense forest and the brown ones in quite sparse forest. And here we clearly see the daily cycle of albedo, so the importance of the shadows, which is shown by the variation with zenith angle, which is actually just the variation throughout the course of a day. And so we have quite strong variations, especially at the sparse forest sites. And now we can test the model against this data. And we do that by running a model at each of the waypoints shown on this plot so that we can directly compare the model results to the measurements. And this is what we got. So two things are striking. First of all, we do not see daily cycles at all. So very obviously, the model cannot capture this impact of the shading on the land surface albedo. And then I'd like to point out that the y-axis of the two plots are not the same. And so actually at the sparse locations, the model is massively overestimating the land surface albedo. And so there is a very clear positive bias for a certain type of forest. And now these results allow us for the first time to track down the reason for these big uncertainties that we find in climate models in replicating this process. So to wrap up, I hope that this talk has taught you something about snow albedo feedback over the boreal forest and why it's a difficult process to understand and to quantify, and climate models are currently struggling with it. I hope you realize that drones are great, but they're also hard work. So the data doesn't come for free. Off-the-shelf solutions do not really work, and we need to be creative with our systems to get something out of it. And yeah, then I hope you realize that so by creating such a new system, we were able to gain quite an innovative data set that really has the potential to advance our understanding of current model performance and hopefully also help us improve it. Yeah, that's as much as I wanted to show. And now I'm open for questions. And again, thank you a lot for having me.